Somewhere in the oldest light the universe ever made, there is a line, a faint, impossible alignment stretching across billions of light years, pointing in a direction that, by all our theories, should not exist. Scientists, half joking and half unsettled, began calling it the axis of evil, because it seems to defy the assumption that the cosmos has no preferred orientation, no special place, no hidden architecture waiting to be found. And yet there it is, etched into the cosmic microwave background, the afterglow of creation itself, a pattern where randomness was expected, a whisper of structure where silence should have been. If these quiet explorations help the night feel gentler, subscribing means more of them will find their way to you. For now, the room can grow still, the breath can slow, and we can begin here, with the light that has traveled 13 billion years to reach us, carrying its strange secret. When we look out into the night sky, we are always looking backward in time, because light takes a certain amount of time to travel from distant objects to our eyes, and so the farther away something is, the older the light we are seeing. The stars in our own galaxy send us light that is perhaps a few hundred or a few thousand years old, while the light from distant galaxies has been traveling for millions or even billions of years before it reaches our telescopes. But there is a kind of light that is older than all of these, a light so ancient that it has been traveling through space since before any stars or galaxies existed, and this light is called the cosmic microwave background, which is perhaps the most important source of information we have about the earliest moments of the universe. The cosmic microwave background, which scientists often abbreviate as the CMB for convenience, is sometimes described as the afterglow of the Big Bang, which is a rather poetic way of capturing what it actually is. To understand where this light comes from, we need to think back to a time when the universe was very young indeed, only about 380,000 years after it began, which sounds like a long time but is really just a tiny fraction of the universe's current age of 13.8 billion years. In those earliest times, the universe was extraordinarily hot and dense, filled with a plasma of charged particles, mostly protons and electrons, that were moving so energetically that they could not settle down and combine into atoms. Light could not travel very far in this environment, because photons kept scattering off the free electrons, bouncing this way and that in a kind of continuous foggy chaos, much like how light scatters inside a very thick cloud and cannot pass straight through. But as the universe expanded, it also cooled, because the energy was spread out over an ever larger volume of space, and eventually the temperature dropped low enough that something quite important could happen. The protons and electrons finally slowed down enough that they could combine to form neutral hydrogen atoms, a process that physicists call recombination even though the particles had never been combined before, which is one of those slightly confusing terms that has stuck around for historical reasons. When the atoms formed, suddenly there were no longer free electrons everywhere for the light to scatter off, and the universe became transparent for the first time. The photons that had been bouncing around in that hot plasma were suddenly free to travel in straight lines across the cosmos, and they have been traveling ever since, for nearly 14 billion years, carrying information about what the universe was like at that moment of transition. This is the light that we call the cosmic microwave background. It is not coming from any particular star or galaxy, but rather from everywhere, from every direction we look in the sky. It is a kind of wall of light that surrounds us completely, the most distant thing we can ever see, because before this light was released the universe was opaque and there is simply no earlier light for us to observe directly. When we detect the cosmic microwave background, we are seeing a snapshot of the infant universe, captured at a moment when it was about 380,000 years old, which makes it by far the oldest light in existence. Now, when this light was first released, it was extremely hot, with a temperature of about 3,000 degrees Kelvin, which is roughly half the temperature of the surface of our Sun. It would have appeared as a brilliant orange-red glow, visible light in the part of the spectrum our eyes can see. But in the billions of years since that time, the universe has continued to expand, and as space itself stretches, it stretches the light traveling through it as well. The wavelength of light gets longer, which means the light shifts toward the red end of the spectrum and beyond, into infrared and then into microwaves. This is why the ancient light that was once visible now appears as microwave radiation, which is a form of light with much longer wavelengths than our eyes can detect, similar to the radiation used in microwave ovens though far less intense. The cosmic microwave background has been stretched so much by the expansion of space that it now has a temperature of only about 2.725 Kelvin, which is just a few degrees above absolute zero, the coldest possible temperature at which all thermal motion would cease. 2.725 Kelvin is extraordinarily cold, and yet this faint warmth pervades all of space, coming from every direction equally, a gentle whisper of heat left over from the universe's fiery beginning. It is the same temperature everywhere to an astonishing degree of precision, which tells us that the early universe was remarkably uniform, with matter and energy spread out very evenly across vast distances. This uniformity is itself something that requires explanation, and cosmologists have developed theories about a period of extremely rapid expansion called inflation that might account for it. But that is a topic for another time. For now, it is enough to appreciate that the cosmic microwave background is there, filling all of space with its ancient and exceedingly faint glow. The story of how scientists first discovered the cosmic microwave background is a rather charming one, because it happened more or less by accident. In the year 1965, two physicists named Arno Pentjes and Robert Wilson were working at Bell Telephone Laboratories in Holmdel, New Jersey, using a large horn-shaped antenna that had originally been built for experiments in satellite communication. The antenna was designed to be very sensitive, capable of picking up extremely faint signals, because satellite communication requires detecting very weak radio waves from spacecraft high above the Earth. Pentjes and Wilson were trying to use this antenna for radio astronomy, and in order to make precise measurements of astronomical sources, they needed to account for all possible sources of noise that might interfere with their observations. As they worked with the antenna, they noticed a persistent hiss of microwave noise that they could not explain or eliminate. It was not very strong, but it was definitely there, a faint excess signal that seemed to come from everywhere in the sky, not from any particular direction. They tried everything they could think of to get rid of it. They pointed the antenna in different directions, and the noise remained the same. They checked all their equipment for possible sources of interference, examining every connection and cable. They even noticed that some pigeons had been nesting inside the horn of the antenna and had left droppings there, and they wondered if perhaps this material might be causing the noise. They carefully cleaned out the antenna, removing the pigeons and what the scientists politely referred to as a white dielectric substance. But the mysterious hiss persisted just as before. Pentjes and Wilson were puzzled, because the noise simply would not go away no matter what they tried. It behaved as if it were coming from the sky itself, from all directions at once, with a temperature that they measured at about 3.5 Kelvin, which was reasonably close to what we now know to be the actual value. They knew they were detecting something real, but they did not immediately understand what it was. Around the same time, not very far away at Princeton University, a group of physicists led by Robert Dicke had been thinking about the theoretical prediction that there should be leftover radiation from the Big Bang, and they were actually building their own antenna to search for it. When Penchers happened to mention the unexplained noise to a colleague, word eventually reached the Princeton group, and they realized that what Penchers and Wilson had found was exactly what they had been looking for. The two discoveries came together beautifully. Penchers and Wilson had the observational evidence, this persistent microwave hiss from all directions, while the Princeton group had the theoretical framework to explain what it meant. Two papers were published side by side, one describing the observations and the other explaining their cosmological significance. The faint noise that had seemed like an annoying experimental problem turned out to be one of the most important discoveries in the history of cosmology, direct evidence that the universe had indeed begun in a hot, dense state and had been expanding and cooling ever since. For this discovery, Arno Penchers and Robert Wilson were awarded the Nobel Prize in Physics in 1978. A recognition of how their careful and persistent work had opened a new window onto the early universe. It is rather wonderful to think that this discovery came about because two scientists refused to ignore a small discrepancy in their data. They could have dismissed the noise as unimportant, as some kind of instrumental effect that was not worth worrying about, but instead they pursued it methodically, checking every possible explanation until they were certain that the signal was real. And in doing so, they stumbled upon the oldest light in the universe, a faint echo of the moment when the cosmos first became transparent and light could travel freely through space. Since that initial discovery, the cosmic microwave background has been studied with increasingly sophisticated instruments, first from the ground and from balloons, and later from space. Satellites such as the Cosmic Background Explorer in 1989, the Wilkinson Microwave Anisotropy Probe in 2001, and the Planck satellite in 2009 have mapped the CMB across the entire sky with extraordinary precision, revealing subtle variations in temperature from one point to another that are only a few parts in 100,000. These tiny fluctuations are the seeds from which all the structure in the universe eventually grew, the slight variations in density that gravity would later amplify into galaxies and clusters of galaxies and all the cosmic architecture we see today. But the cosmic microwave background is not merely useful for understanding how structure formed. It is also a kind of cosmic Rosetta Stone, encoding information about the fundamental properties of the universe itself, its geometry, its composition, its age, and its rate of expansion. By studying the patterns in the CMB, cosmologists have been able to determine that the universe is approximately 13.8 billion years old, that it is geometrically flat to a very high precision, and that it contains a mix of ordinary matter, and dark energy in specific proportions. All of this information is carried in that ancient light, waiting to be decoded by patient observation and careful analysis. And so the cosmic microwave background remains one of the most important tools we have for understanding the cosmos. It is always there, coming from every direction, a faint and gentle glow that has been traveling toward us since the universe was young. When we detect it today, we are seeing light that has journeyed for nearly 14 billion years, stretched by the expansion of space from visible orange-red to invisible microwaves, cooled from thousands of degrees to just a few degrees above absolute zero. It is the oldest light we will ever see, a message from the beginning of time, and it arrived at our doorstep disguised as noise, waiting for two curious scientists in New Jersey to clean out the pigeon droppings and listen carefully to what the universe was trying to tell them. When we look out into the vastness of space, we are really looking back in time, because light travels at a finite speed, and the farther away an object is, the longer its light has taken to reach us. And when we look very far indeed, past all the nearby galaxies and past the distant quasars and past even the faintest smudges of light that our most powerful telescopes can detect, we eventually reach a kind of boundary, not a physical wall but a moment in time, beyond which the universe becomes opaque to light. This boundary marks the era when the universe was so hot and so dense that atoms could not yet form, and free electrons scattered every photon that tried to travel anywhere, creating a kind of brilliant fog that filled all of space. And when we observe this boundary today, we see it as a faint glow of microwave radiation coming from every direction in the sky, the remnant warmth of that ancient fog, now cooled and stretched by the expansion of the universe across nearly 14 billion years. This is the cosmic microwave background, and it is perhaps the most important single piece of evidence we have about the conditions of the early universe. For a very long time, scientists have operated under an assumption that has proven remarkably useful, an assumption so fundamental that it underlies almost all of modern cosmology. This assumption is called the cosmological principle, and it states, in essence, that the universe is homogeneous and isotropic on sufficiently large scales. Homogeneity means that if you were to travel to some distant region of the universe, billions of light-years from here, you would find that the local conditions there, the density of matter, the types of structures present, the general character of things, would be statistically similar to what we observe in our own cosmic neighborhood. Isotropy means that when we look out from our vantage point here on Earth, the universe appears the same in every direction, with no special axis or preferred orientation, no cosmic north or south, no direction that is fundamentally different from any other. These two ideas together suggest that there is nothing particularly special about our location in the cosmos, that we do not occupy a privileged position, and that the laws of physics and the large-scale properties of the universe are the same everywhere. This principle has deep roots in the history of science, going back at least to the Copernican revolution, which removed the Earth from the center of the solar system and began the long process of recognizing that we are not at the center of anything in particular. Over the centuries, this idea has been extended further and further, first removing the Sun from any special position in the galaxy, then recognizing that our galaxy is just one of billions, and finally arriving at the cosmological principle, which asserts that on the grandest scales, there is no center at all, no edge, no preferred location, just an endless expanse of space that looks more or less the same wherever you happen to be. It is a humbling idea in some ways, but also a simplifying one, because if the universe really is the same everywhere and in every direction, then we can describe its behavior with relatively simple mathematical models. Albert Einstein, when he developed his general theory of relativity in 1915, created a new framework for understanding gravity, not as a force acting between objects, but as a curvature of space-time itself, caused by the presence of mass and energy. This theory was revolutionary in many ways, but one of its most striking features was that it could be applied to the universe as a whole, allowing scientists for the first time to construct mathematical models of the entire cosmos. And when Einstein and others began to explore what his equations implied about the universe, They found that the simplest solutions, the ones that were most mathematically tractable and most elegant, were those that assumed the universe was homogeneous and isotropic. These solutions, known as the Friedmann-Lemaitre-Robertson-Walker metrics, became the foundation of modern cosmology, describing a universe that expands uniformly in all directions, with matter distributed evenly on large scales, and no preferred direction or special location. Today, the standard model of cosmology is known as the lambda-CDM model, where lambda refers to the cosmological constant, which accounts for the mysterious dark energy that seems to be causing the expansion of the universe to accelerate, and CDM stands for cold dark matter, the invisible substance that provides most of the gravitational scaffolding for galaxies and galaxy clusters. This model has been extraordinarily successful at explaining a wide range of observations, from the distribution of galaxies across the sky to the detailed properties of the cosmic microwave background. But it is important to remember that the lambda-CDM model, like Einstein's original cosmological solutions, rests upon the assumption of the cosmological principle. If the universe were not homogeneous and isotropic on large scales, if there were significant variations in density or some preferred direction built into the fabric of space itself, then the mathematics would become far more complicated, and many of our confident conclusions about the age, composition, and history of the universe would need to be reconsidered. Given this assumption, scientists had very specific expectations about what the cosmic microwave background should look like, because it represents the light from a time when the universe was extremely uniform, filled with a nearly featureless plasma of particles and radiation. The CMB was expected to be almost perfectly smooth, with the same temperature in every direction to a remarkable degree of precision. The actual temperature of this radiation, as we measure it today, is about 2.7 Kelvin, just a few degrees above absolute zero, and this temperature was expected to be the same whether you pointed your detector toward the constellation Orion or toward the Southern Cross, toward the center of our galaxy or toward the emptiest voids between galaxy clusters. Any deviations from this perfect uniformity were expected to be extraordinarily small, perhaps 1 part in 100,000, which would correspond to temperature differences of just a few millionths of a degree. These tiny fluctuations were not merely expected, they were required, because without some small variations in the density of the early universe, there would be no way for gravity to begin the slow process of pulling matter together into the galaxies and clusters we observe today. If the early universe had been perfectly uniform, with matter distributed with absolute evenness everywhere, then there would have been no reason for any particular region to start collapsing before any other, and the universe would have remained a featureless expanse forever. So cosmologists knew that there had to be some small ripples in the primordial plasma, quantum fluctuations perhaps, stretched to cosmic scales by the rapid expansion of inflation, and imprinted onto the cosmic microwave background as tiny variations in temperature. But these fluctuations were expected to be randomly distributed, scattered across the sky with no particular pattern, no alignment, no preferred direction, just the gentle statistical noise of a universe that was, on average, the same everywhere. Detecting these tiny fluctuations was an enormous technical challenge, because they are so small compared to the overall brightness of the microwave background, and because there are many other sources of microwave radiation that can contaminate the measurements, including our own galaxy and even the instruments themselves. For decades, scientists worked to improve their detectors and their techniques, gradually pushing down the limits of what they could observe, but the fluctuations remained elusive, hidden beneath the noise. The breakthrough came with a satellite called COBE, which stands for Cosmic Background Explorer. This mission had been in development for many years, and it represented a major commitment of resources and expertise from NASA and the scientific community. The project was led by two American physicists, John Mather and George Smoot, who had been working on the problem of measuring the cosmic microwave background for much of their careers. Mather was responsible for the overall design of the satellite and for one of its key instruments, which would measure the spectrum of the microwave background with unprecedented precision. Smoot was responsible for another instrument, called the differential microwave radiometer, which was specifically designed to look for tiny differences in temperature between different parts of the sky. The COBE satellite was launched on the 18th of November in 1989 from Vandenberg Air Force Base in California, aboard a Delta rocket that carried it into a polar orbit around the Earth. From this vantage point, the satellite could scan the entire sky over the course of a year, building up a detailed map of the microwave background while staying above most of the interfering radiation from the Earth's atmosphere. The instruments on board were cooled to extremely low temperatures to reduce their own thermal noise, and the data were carefully analyzed to remove contamination from the Milky Way and other foreground sources. The results from COBE exceeded all expectations. Mather's instrument confirmed that the spectrum of the cosmic microwave background matched a perfect blackbody curve with astonishing precision, exactly as the Big Bang theory predicted, providing strong evidence that this radiation really was the afterglow of the hot, dense early universe. But it was Smoot's instrument that produced the most dramatic discovery. After painstaking analysis of the data, the team found that there were indeed tiny fluctuations in the temperature of the microwave background, variations of about 1 part in 100,000, just as the theorists had predicted. The announcement was made in April of 1992, at a meeting of the American Physical Society, and it caused an immediate sensation in the scientific world. George Smoot, when asked to describe the significance of this discovery, compared it to looking at the face of God. This was not a statement about religion, but rather an expression of the profound sense of awe that the scientists felt at having glimpsed the seeds of all cosmic structure, the tiny irregularities in the early universe that would eventually grow into galaxies and clusters and superclusters over billions of years. It was a moment of connection with the very beginning of things, a direct observation of the conditions that existed when the universe was only a few 100,000 years old, long before any stars had formed, long before any planets or life could exist. The importance of this discovery was recognized by the scientific community with the highest honor available, the Nobel Prize in Physics, which was awarded to John Mather and George Smoot in 2006. The Nobel Committee cited their work for its contribution to our understanding of the origin of galaxies and the structure of the universe, and the prize was a fitting recognition of decades of careful work by two dedicated scientists and their many collaborators. But even as the celebrations continued, cosmologists were already looking ahead to the next generation of experiments, which would map the cosmic microwave background with even greater precision and search for ever more subtle features in its pattern. And it was here that some unexpected findings would begin to emerge, hints of structures and alignments that did not quite fit the simple picture of a universe that looks the same in every direction. But that is a matter for later consideration. And for now, it is enough to rest with the knowledge that the cosmic microwave background exists, that its fluctuations have been measured, and that these measurements have confirmed, at least to a first approximation, the beautiful simplicity of a universe that is, on the grandest scales, remarkably uniform and without any obvious preferred direction. In the closing months of the 20th century, while the world prepared for a new millennium and all the symbolic weight that such transitions carry, a team of scientists and engineers was completing work on a spacecraft that would spend the better part of a decade listening to the oldest light in existence. This spacecraft, which would eventually bear the name of a physicist who dedicated much of his life to understanding the cosmic microwave background, was designed to measure temperature differences so slight that they would be invisible to any instrument built just a generation earlier. The mission represented a kind of patient ambition, the sort that requires years of planning and construction before a single measurement can be made, and it would ultimately produce a portrait of the infant universe that remains one of the most studied images in the history of astronomy. The Wilkinson Microwave Anisotropy Probe, known by the abbreviation WMAP, lifted off from Cape Canaveral Air Force Station on the 30th of June in the year 2001. It rose on a Delta II rocket through the humid Florida air, climbing through the atmosphere and beginning a journey that would take it far beyond the orbit of the Moon, to a point in space where it could observe the entire sky without the Earth constantly swinging into view. The launch occurred in the early afternoon, local time, and the spacecraft separated from its rocket stages in the expected sequence, beginning the long cruise toward its operational position. There was something almost unremarkable about the launch itself, in the way that the most consequential scientific missions often proceed without fanfare, following checklists and procedures refined over decades of spaceflight experience. The probe was named after David Todd Wilkinson, a Princeton University cosmologist who had been one of the pioneers in the study of the cosmic microwave background. Wilkinson had been involved in attempts to detect this ancient radiation as early as the 1960s, and he had spent decades refining the instruments and techniques needed to measure its properties with increasing precision. He was a founding member of the WMAP science team and had contributed substantially to the design of the mission, but he did not live to see the spacecraft reach its destination or return its first measurements. Wilkinson passed away in September of 2001, just 3 months after the launch, following a struggle with cancer. The decision to rename the mission in his honor came in 2003, when the first results were released, transforming what had been called the Microwave Anisotropy Probe into the Wilkinson Microwave Anisotropy Probe. It was a quiet tribute to a scientist who had devoted his career to understanding the faint signals that the spacecraft would now detect. The destination for WMAP was a location known as the Second Lagrange Point, or L2, which lies approximately 1.5 million kilometers from Earth in the direction away from the Sun. Lagrange points are positions in space where the gravitational influences of two large bodies, in this case the Earth and the Sun, combine with the centrifugal effect of orbital motion to create a kind of gravitational equilibrium. An object placed at one of these points can maintain a relatively stable position with respect to the two larger bodies, requiring only modest amounts of fuel for occasional adjustments. The L2 point is particularly useful for astronomical observations because it allows a spacecraft to keep the Sun, Earth, and Moon all on roughly the same side, which means that a sunshield can block light and heat from all three sources simultaneously. This arrangement permits the sensitive instruments on board to operate at extremely cold temperatures, which is essential for detecting the faint microwave radiation from the cosmic microwave background without interference from warmer nearby objects. WMAP arrived at L2 in October of 2001 and began its scientific observations the following year. The spacecraft carried two back-to-back telescopes that fed microwave signals to a set of radiometers, instruments capable of measuring the intensity of microwave radiation with extraordinary precision. Rather than producing images in the conventional sense, the probe measured the difference in temperature between 2 points on the sky separated by approximately 140 degrees, and by sweeping across the entire celestial sphere over a period of 6 months, it built up a complete map of the microwave background. The spacecraft rotated slowly, completing one full spin every 2 minutes or so, while also precessing around a larger cone that allowed it to cover the entire sky systematically. This observing strategy was designed to minimize the effects of systematic errors and to ensure that every part of the sky was measured multiple times under slightly different conditions. The principal investigator for the WMAP mission was Charles Bennett, an astrophysicist at Johns Hopkins University in Baltimore, Maryland. Bennett had been involved in the earlier COBE mission that first detected the tiny temperature variations in the cosmic microwave background, and he brought that experience to the design and leadership of WMAP. Under his direction, the science team developed the procedures for analyzing the vast quantities of data that the spacecraft would return, and for extracting from those data the fundamental parameters that describe the structure and evolution of the universe. The team included dozens of scientists from institutions across the United States and around the world, each contributing expertise in areas ranging from instrument calibration to theoretical cosmology. WMAP operated continuously from 2001 until 2010, a span of 9 years during which it returned measurements of steadily increasing precision. The first results, released in 2003, were already the most detailed observations of the cosmic microwave background ever made, but the team continued to refine their analysis as more data accumulated. Each additional year of observations allowed them to average out the random noise that inevitably contaminates any measurement, revealing ever subtler features in the temperature patterns of the ancient radiation. By the time the mission concluded, WMAP had produced a full sky map with an angular resolution of about 1/5 of a degree, fine enough to distinguish features separated by roughly 4 times the apparent diameter of the full moon. To extract meaningful information from this map, scientists employ a mathematical technique known as spherical harmonic analysis, which is a way of decomposing any pattern on the surface of a sphere into a set of simpler component patterns. The method is analogous to the process by which a complex sound can be broken down into its constituent musical notes, with each note corresponding to a particular frequency of vibration. When you hear a chord played on a piano, your ear receives a single complicated waveform, but your brain, and more precisely the cochlea in your inner ear, separates that waveform into its component frequencies, allowing you to perceive the individual notes that make up the chord. Spherical harmonic analysis does something similar for patterns on a sphere, separating the complicated map of temperature variations into a series of simpler patterns, each characterized by a particular spatial frequency. In the language of spherical harmonics, each component pattern is identified by a number called the multipole moment, typically denoted by the letter L. The lowest multipole, L equals 0, is called the monopole, and it represents the average temperature across the entire sky, a single uniform value with no variation from place to place. The next multipole, L equals 1, is the dipole, which represents a pattern in which one hemisphere of the sky is slightly warmer than the opposite hemisphere. As we discussed earlier, the observed dipole in the cosmic microwave background is dominated by the Doppler effect arising from our motion through space, and so it is usually removed from the analysis to reveal the underlying primordial variations. The subsequent multipoles, with L equals 2, 3, 4, and so on, represent patterns with increasingly fine angular structure, each dividing the sky into a larger number of regions with alternating slightly warmer and slightly cooler temperatures. The multipole with L equals 2 is called the quadrupole, and it represents the largest scale genuine variation in the cosmic microwave background after the monopole and dipole are accounted for. You might visualize the quadrupole pattern as dividing the sky into 4 broad regions, like the segments of an orange cut into quarters, though the precise shape depends on the particular combination of spherical harmonics that contribute to it. The next multipole, with L equals 3, is called the octupole, and it represents a pattern with 8 such regions, again arranged in a characteristic way across the celestial sphere. These low multipoles, the quadrupole and octupole especially, correspond to the very largest structures in the cosmic microwave background, spanning many tens of degrees across the sky. The reason scientists pay particular attention to these large-scale patterns is that they carry information about the conditions of the early universe on the largest possible scales. Features in the cosmic microwave background that span only a degree or two correspond to regions of space that had time to interact with each other through physical processes during the first few 100,000 years after the Big Bang. But the very largest features, those represented by the lowest multipoles, correspond to scales so vast that different parts of those features could never have exchanged any physical influence, even at the speed of light, during the time between the Big Bang and the release of the microwave background. According to the simplest theoretical models, these primordial variations should be the product of quantum fluctuations that occurred during a period of extraordinarily rapid expansion called inflation, and those fluctuations should be random in nature, showing no preferred directions or alignments. When the WMAP team began to analyze their data, they expected to find exactly this sort of randomness in the large-scale patterns. The quadrupole and octupole, being the largest scale variations after the dipole, should each point in whatever direction chance happened to dictate during those earliest moments of cosmic history. There was no known physical mechanism that would cause these patterns to align with each other, or with any particular direction in space, and so the scientists anticipated that the orientations of the quadrupole and octupole would be as uncorrelated as 2 arrows thrown into the air and allowed to land wherever they might. The universe, after all, is thought to be isotropic on the largest scales, meaning that it should look statistically the same in every direction, with no special axes or planes to single out one orientation over another. This expectation of randomness was not merely an assumption of convenience, but rather a prediction that follows directly from the inflationary model of the early universe, a model that has been remarkably successful in explaining many other features of the cosmic microwave background. Inflation posits that the tiny quantum fluctuations that seeded all the structure we see today were generated in a process that knew nothing about spatial directions, producing variations that were statistically identical regardless of where you looked on the sky. If this picture is correct, then the orientations of the low multipoles should be distributed uniformly across all possible directions, and any particular alignment between them should be no more or less likely than any other. The WMAP team, therefore, approached their analysis with the reasonable expectation that the quadrupole and octupole would point in different directions, as independent as the outcomes of 2 separate coin tosses. The spacecraft continued its patient work, rotating gently at the L2 Lagrange point, its twin telescopes sweeping across the sky month after month and year after year. The data flowed back to Earth in a steady stream, recorded by receiving stations and processed by the science team in Baltimore and elsewhere. Each measurement was carefully calibrated, corrected for instrumental effects, and combined with millions of others to build up the full sky map that would become one of the iconic images of modern cosmology. The team worked methodically, checking their results against simulations and theoretical predictions, and preparing to release their findings to the scientific community and to the world. What they found in the large-scale patterns of the cosmic microwave background would give pause to cosmologists for years to come, though the significance of that discovery would be debated and re-examined many times over. For now, the data were being gathered, the map was becoming clearer, and the universe was quietly revealing something that no one had quite expected. When the Wilkinson Microwave Anisotropy Probe began returning its exquisitely detailed measurements of the cosmic microwave background in the early years of the 2000s, cosmologists around the world settled in to analyze what was, by any reasonable measure, one of the most beautiful datasets in the history of science. The probe had been launched in June of 2001, and it had traveled to a special point in space called the second Lagrange point, about 1.5 million kilometers from Earth, where it could observe the entire sky without the interference of our planet's warmth or the glare of the sun. From this vantage point, it spent years patiently measuring the faint glow of radiation that had been traveling through the universe for nearly 14 billion years, and the maps it produced were stunning in their precision, revealing the tiny temperature fluctuations in the ancient light with a clarity that had never before been achieved. The first full-year data release came in 2003, and the scientific community received it with enormous enthusiasm, because the measurements confirmed so many of the predictions of the standard cosmological model with remarkable accuracy. The universe appeared to be flat, or very nearly so, and the proportions of ordinary matter, dark matter, and dark energy matched what theorists had expected. The angular power spectrum, which describes how the temperature fluctuations are distributed across different scales on the sky, showed the series of peaks and troughs that had been predicted by the theory of acoustic oscillations in the early universe, those ancient sound waves frozen into the pattern of the cosmic microwave background. In most respects, the data was a triumphant confirmation of our understanding of the cosmos, and there was a general sense of satisfaction that the standard model of cosmology was proving itself to be a reliable guide to the structure and history of the universe. And yet, as researchers began to examine the data more closely, certain unexpected features began to emerge, features that did not fit neatly into the elegant theoretical framework that had otherwise performed so well. These anomalies appeared most clearly in the lowest multipoles of the cosmic microwave background, which is to say the largest scale patterns in the temperature fluctuations, the ones that stretch across vast portions of the sky rather than appearing as small hot and cold spots. The very largest of these patterns are described mathematically using spherical harmonics, and the first few multipoles, known as the quadrupole and the octuple, represent structures that span roughly 90 degrees and 60 degrees across the sky respectively. These are enormous patterns, comparable in angular size to the distance from the horizon to the point directly overhead, and they encode information about the very largest scales of structure in the observable universe. When cosmologists examined these large-scale patterns in the WMAP data, they found something rather puzzling. The quadrupole, which should have been the second most prominent large-scale pattern after the uniform background temperature itself, appeared to be significantly weaker than expected, with much less variation in temperature than the standard model predicted. This was curious, but perhaps not alarming on its own. since statistical fluctuations can sometimes produce unusual results. And the universe, after all, is the only one we have to observe. But the more troubling discovery came when researchers noticed that the quadrupole and octuple patterns were not oriented randomly with respect to each other, as one would expect if the universe were truly isotropic, meaning the same in all directions. Instead, these two patterns appeared to be aligned with each other in a way that was highly improbable under the assumptions of standard cosmology. The papers that first highlighted this alignment began appearing in 2003 and continued through 2005, as different research groups independently confirmed and explored the anomaly using various statistical techniques. The alignment was subtle enough that it required careful mathematical analysis to identify, but once it was found, it was difficult to dismiss. The quadrupole pattern, despite its low amplitude, had a preferred axis, a direction in space along which its structure was organized, and the octuple pattern had its own preferred axis as well. Under the standard cosmological model, there was no reason to expect these axes to point in similar directions, since the fluctuations in the cosmic microwave background were thought to arise from quantum processes in the very early universe that should have been completely random and uncorrelated at these large scales. The universe, according to the principle of isotropy, should look statistically the same in every direction, with no special axes or preferred orientations embedded in its structure. At Imperial College London, two physicists named Kate Land and João Maguijo undertook a particularly thorough analysis of this alignment, examining the WMAP data with a suite of statistical tests designed to quantify just how unusual it was. Their work, published in Physical Review Letters in 2005, confirmed what others had suspected, that the alignment between the quadrupole and octuple was extraordinarily unlikely to occur by chance. They calculated that the probability of such an alignment appearing randomly in an isotropic universe was less than 0.1%, which is to say that if you generated 1,000 different realizations of a statistically isotropic cosmic microwave background, you would expect to see an alignment this strong in fewer than one of them. This was not the sort of statistical fluke that cosmologists could easily wave away. Land and Maguijo, recognizing the profound implications of their findings for the foundations of modern cosmology, chose to give this anomaly a deliberately provocative name. They called it the axis of evil, borrowing a phrase that had recently entered the political lexicon with rather different connotations. And they did so not to sensationalize their work but to emphasize just how troubling this alignment was for the standard theoretical framework. The term was meant to highlight the fact that if this alignment were real, and not the result of some systematic error or local contamination, then it would represent a serious challenge to one of the fundamental assumptions of cosmology, the assumption that the universe has no preferred directions, that space is isotropic on the largest scales. An axis running through the cosmos, along which the largest patterns in the primordial radiation were organized, would be a deeply uncomfortable thing for cosmologists to explain. What made the situation even more unsettling was the particular direction in which this axis appeared to point. When Land and Maguijo and other researchers examined the orientation of the aligned quadrupole and octuple, they found that it was not pointing off toward some random and unremarkable patch of distant space. Instead, the axis appeared to be oriented suspiciously close to the plane of our own solar system's orbit around the Sun, the plane that astronomers call the ecliptic. Furthermore, the axis seemed to have some relationship to the direction of our motion through space, the direction in which the Earth and Sun and entire solar system are traveling relative to the cosmic microwave background itself. This was, to put it mildly, unexpected. The ecliptic plane is a purely local feature of our particular corner of the universe, a consequence of the accidental orientation of the cloud of gas and dust from which our solar system formed some 4.5 billion years ago. It has no cosmological significance whatsoever, no connection to the physics of the early universe or the processes that generated the cosmic microwave background nearly 14 billion years ago. The direction of our motion through space, while determined by the gravitational influences of nearby galaxies and larger structures, is similarly a local phenomenon with no obvious relationship to the primordial fluctuations imprinted on the ancient light. And yet here was an apparent alignment between patterns in the cosmic microwave background, patterns that should reflect the structure of the entire observable universe, and the orientation of our own small planetary system orbiting an ordinary star in an unremarkable galaxy. This coincidence raised immediate suspicions that something might be wrong with the data rather than with our understanding of cosmology. The most natural explanation for an alignment between cosmic structures and local solar system geometry would be that the alignment was not real at all, but rather an artifact of the measurement process, some systematic error that had crept into the data and created a spurious pattern. The WMAP satellite, after all, was orbiting the Sun along with the Earth, and its observations were necessarily made from within the solar system, looking out through whatever material might exist in our local environment. If there were sources of microwave radiation within the solar system or nearby in our galaxy that had not been properly accounted for, they might create artificial patterns in the maps that could mimic cosmological signals. Foreground contamination from our own Milky Way galaxy was a particular concern. The galaxy is filled with dust and gas that emit radiation across a wide range of wavelengths, including microwaves, and this foreground emission must be carefully removed from the data before the cosmic microwave background can be studied. The galactic plane, where most of this contaminating material is concentrated, cuts across the sky at a certain angle, and the process of subtracting this foreground requires sophisticated modeling and can potentially introduce errors if the models are imperfect. Cosmologists initially hoped that the axis of evil might simply be a residual effect of imperfect foreground subtraction, a ghostly imprint of the Milky Way structure left behind in the maps after the cleaning process. Similarly, there was the possibility that zodiacal light, the faint glow of sunlight scattered by dust particles in the plane of the solar system, might somehow be contributing microwave emission that could affect the measurements. The zodiacal dust cloud is concentrated in the ecliptic plane, and if it were emitting or scattering microwaves in a way that had not been anticipated, this could potentially explain why the anomalous alignment seemed to be oriented along the ecliptic. Researchers spent considerable effort investigating these possibilities, developing new techniques for foreground removal and testing whether the alignment persisted when different methods were used to clean the data. Other potential systematic effects were also considered. The scanning strategy of the WMAP satellite, the particular pattern of observations it used to build up its maps of the sky, could potentially introduce subtle artifacts if not properly corrected. The satellite rotated and precessed in a complicated dance designed to ensure complete sky coverage, but any imperfections in the instrument or the data processing pipeline might leave their mark on the final maps. The beam shape of the satellite's detectors, the precise pattern of sensitivity across the sky for each measurement, could also introduce subtle distortions if not perfectly characterized. Each of these potential sources of systematic error was examined and tested, and each time the alignment stubbornly refused to disappear. The research groups working on this problem were not hoping to overturn modern cosmology. Quite the contrary. Most of them would have been greatly relieved to find a mundane explanation for the axis of evil that would allow the standard model to remain unchallenged. The assumption of isotropy, the idea that the universe looks the same in all directions on large scales, is not merely a convenient simplification but a foundational principle upon which the entire framework of modern cosmology is built. The equations that govern the expansion of the universe, the calculations that determine the age and composition of the cosmos, the models that explain the formation of galaxies and the distribution of matter, all of these depend in essential ways on the assumption that space is homogeneous and isotropic. To discover that the universe has a preferred axis, a special direction embedded in its structure from the earliest moments, would require a fundamental rethinking of cosmological theory. And so cosmologists approached the axis of evil with considerable caution, neither dismissing it out of hand nor accepting it uncritically, but rather subjecting it to every test they could devise in the hope of understanding its origin. The alignment was unusual, statistically improbable, and troublingly oriented toward local solar system geometry, all of which suggested that something might be wrong somewhere, either with our measurements, our foreground models, or our understanding of the universe. In the years following the initial discovery, this question would remain open, with new data and new analyses adding layers of complexity to an already puzzling situation. The universe, it seemed, had presented cosmologists with a gentle but persistent mystery, a pattern that should not exist, an alignment that defied easy explanation, an axis that would continue to demand attention and careful thought for years to come. And so the years passed, as they do, and the scientific community continued to study the curious patterns that WMAP had revealed in the ancient light. And all the while, preparations were underway for a new mission, one that would examine the cosmic microwave background with instruments of unprecedented precision. And this mission would come to be known as Planck, named after the German physicist Max Planck, whose work on black-body radiation at the turn of the 20th century had helped give birth to quantum mechanics, and it seemed fitting that a satellite bearing his name would study the most perfect black-body spectrum ever observed in nature, that faint thermal glow left over from when the universe was young and hot and filled with light that had nowhere to go until the fog of electrons finally cleared. The European Space Agency led the development of the Planck satellite, working in collaboration with national space agencies across Europe and with significant contributions from NASA as well, and the project represented years of careful planning and engineering, the construction of instruments that pushed the boundaries of what was technically achievable at the time. And when the launch date finally arrived, it was the 14th of May in the year 2009. A day that likely passed without much notice for most people going about their ordinary lives. But for the scientists and engineers who had devoted years to this endeavor, it was a moment of considerable anticipation, as their creation sat atop an Ariane 5 rocket at the Guiana Space Center in Kourou, French Guiana, that European spaceport nestled on the northeastern coast of South America, where the proximity to the equator provides a helpful boost to rockets heading into orbit. And when the engines ignited and the rocket rose through the atmosphere trailing fire and steam, the Planck satellite was on its way to a vantage point from which it would survey the entire sky. The satellite traveled to a location known as the second Lagrange point, or L2, which sits about 1.5 million kilometers from Earth in the direction away from the Sun. And at this special point, a spacecraft can orbit the Sun in lockstep with our planet, maintaining a relatively stable position that keeps both the Sun and the Earth in roughly the same direction, which proves useful when you want to point sensitive instruments at the cold depths of space without having to worry too much about stray heat from nearby warm objects. And from this distant perch, Planck began its patient work of mapping the microwave sky, scanning round and round, gradually building up a picture of the cosmic microwave background radiation that would surpass anything that had come before. What made Planck so special? What allowed it to see the ancient light with such clarity? Was the remarkable sensitivity of its instruments. And at the heart of this sensitivity was temperature, or rather, the absence of it, because the detectors aboard Planck were cooled to temperatures so low that they seem almost impossible to comprehend. Temperatures approaching 1/10 of a Kelvin, which is to say 1/10 of a degree above absolute zero. That theoretical limit where all thermal motion ceases and matter surrenders whatever warmth it might have held. And at the time of its operation, these detectors were the coldest known objects in space, colder than the cosmic microwave background itself, colder than the dark voids between the stars, colder than anything that nature had produced anywhere in the observable universe. And this extraordinary coldness was essential because the detectors needed to sense the faintest differences in microwave radiation without being confused by their own thermal noise, like trying to hear a whisper in a quiet room rather than in a bustling crowd. Achieving such temperatures in the vacuum of space required a sophisticated cooling system that worked in stages, each stage bringing the temperature down further, using a combination of passive cooling through radiators that shed heat into the cold of space, and active cooling using helium and hydrogen, until finally the most sensitive detectors reached that remarkable 1/10 of a Kelvin. And maintaining these temperatures over the months and years of the mission was itself a significant engineering achievement, a testament to the ingenuity of the teams who designed and built the spacecraft. And the detectors rewarded this effort by delivering measurements of exquisite precision, mapping the tiny temperature variations in the cosmic microwave background with a resolution and accuracy that far exceeded what WMAP had been able to achieve. The Planck collaboration was a vast enterprise, bringing together scientists from more than 100 institutions around the world. Researchers in cosmology and astrophysics and data analysis and instrument design, all working together to extract meaning from the river of data flowing back from that cold and distant satellite. And the process of analyzing this data was painstaking and methodical, requiring careful attention to all the sources of contamination and error that might distort the cosmic signal. And the collaboration developed sophisticated techniques for subtracting the foreground emissions from our own galaxy and from other sources, peeling away these layers to reveal the primordial pattern beneath. And when the results were finally ready to be shared with the world, they came in stages, with major releases in the years 2013 and 2015. Each release accompanied by dozens of scientific papers exploring different aspects of what Planck had found. The quality of the Planck maps was immediately apparent to anyone who compared them with earlier observations. The resolution sharper, the details finer, the tiny fluctuations in temperature mapped with a precision that allowed cosmologists to measure the fundamental parameters of the universe with unprecedented accuracy. And these measurements largely confirmed the standard model of cosmology, that picture of a universe that began in a hot, dense state and expanded and cooled over billions of years. A universe dominated by dark energy and dark matter, with ordinary matter making up only a small fraction of the total. And yet, amid all this confirmation of expectations, there was something else. Something that caused furrowed brows and lengthy discussions at conferences and in the pages of scientific journals. The anomalies persisted. That strange alignment that WMAP had revealed. The curious way the largest patterns in the cosmic microwave background seemed to line up with the geometry of our solar system. The feature that had been half-jokingly named the axis of evil. It was still there in the Planck data, still pointing in roughly the same direction, still raising the same uncomfortable questions about whether it was a genuine feature of the cosmos or some subtle systematic effect that had somehow escaped detection. And the fact that it appeared in data from two completely independent missions, using different instruments and different analysis techniques, made it harder to dismiss as a mere artifact, though of course scientists remained cautious, as they should, about drawing conclusions from features that hovered at the edges of statistical significance. And Planck revealed other anomalies as well, features that had been hinted at in the WMAP data but now stood out more clearly, and among these was something called the hemispherical power asymmetry, which is a rather technical way of describing a curious lopsidedness in the cosmic microwave background, a subtle difference between one half of the sky and the other. And when scientists measured the strength of the temperature fluctuations in different regions of the sky, they found that one hemisphere showed slightly stronger fluctuations than the other, as though the cosmic variation was distributed unevenly across the heavens. And this asymmetry was not large, just a few % difference between the two halves, but it was there in the data, persistent and unexplained, and in a universe that was supposed to be statistically the same in every direction. Such a lopsidedness was puzzling. There was also the matter of the cold spot, a feature that had drawn attention in the WMAP era and now appeared with even greater clarity in the Planck maps. And this cold spot was exactly what its name suggested, a region of the cosmic microwave background that was colder than its surroundings. But what made it noteworthy was its size and its depth, because this was not merely a typical fluctuation of the sort that peppered the entire sky, but rather an unusually large and unusually cold region, spanning roughly 5 degrees across the sky, which might not sound like much until you remember that the full moon appears only about half a degree across. So this cold spot was about 10 times wider than the full moon, a substantial patch of ancient sky that was cooler than the surrounding regions by an amount that seemed improbable given the statistical properties of the rest of the microwave background. The cold spot lies in the direction of the constellation Eridanus, that long winding river of stars that meanders through the southern sky. And when you look toward that part of the heavens on a clear dark night, you see nothing unusual, just scattered stars like any other part of the Milky Way. But behind those stars, far beyond them, at the very edge of the observable universe, the cosmic microwave background carries this curious cold signature, and scientists proposed various explanations for what might cause such a feature, some suggesting it might be the imprint of an unusually large void in the cosmic web, a region where galaxies are sparse and the integrated Sachs-Wolf effect might create a cold spot as photons pass through, though later studies cast doubt on whether any known void was sufficient to explain the observed temperature deficit, and others proposed more exotic explanations. Though, as always in science, extraordinary claims require extraordinary evidence. What struck many researchers about these anomalies, what made them worthy of continued attention and study, was not that any single one of them was overwhelmingly statistically significant, for in truth they were not, but rather that they existed at all and that they persisted across multiple independent observations. And when scientists talk about statistical significance, they often use the language of sigmas, which refers to standard deviations, a measure of how unusual a result is compared to what you would expect from random chance, and the various anomalies in the cosmic microwave background, the alignment with the ecliptic, the hemispherical asymmetry, the cold spot. These features appeared at roughly the 2 to 3 sigma level, which means they were the sort of thing you might expect to see by chance, perhaps once in 100 trials, or once in a few hundred, depending on the specific measurement. Now, 2 or 3 sigma is not the standard that physicists typically require to claim a discovery. For that they usually want 5 sigma, meaning odds of roughly 1 in a million that the result is a fluke. And so the cosmic microwave background anomalies remained in a kind of limbo, too persistent to ignore, too marginal to confirm, hovering at the threshold of significance like a distant figure at the edge of vision that might be real or might be a trick of the light. And this uncertainty was in some ways fitting, because science often proceeds through such ambiguous territory, through years or decades of accumulating evidence before a picture finally becomes clear. The fact that these anomalies appeared in both WMAP and Planck data was significant precisely because the 2 missions were so different in their design and operation. Because WMAP was a NASA mission launched in 2001 with instruments that were state-of-the-art for their time, and Planck was a European mission launched 8 years later with instruments that were far more sensitive and that operated at those remarkably cold temperatures. And the analysis pipelines were developed by different teams using different methods, and the foreground subtraction techniques evolved and improved over the years. And yet through all these changes and improvements, the anomalies remained, like a persistent pattern that refused to wash out. And this persistence across independent observations spanning more than a decade of work was what gave the anomalies their staying power in the scientific discourse. There was always the possibility, of course, that some subtle systematic effect had escaped detection in both missions, some contamination or calibration error that coincidentally produced similar features in both datasets. And scientists took this possibility seriously, scrutinizing their analysis methods, testing their results against simulations, looking for any mundane explanation that might account for what they saw. And some researchers published papers arguing that certain anomalies could be explained by statistical or methodological effects, while others published papers arguing the contrary. And this back and forth was healthy, the normal process by which science examines its own findings and tests them against alternative explanations. The Planck collaboration itself was careful in how it presented these results, acknowledging the anomalies while remaining cautious about their interpretation, noting that features at the 2 to 3 sigma level were not uncommon when you looked at enough different statistics, and that the human mind has a tendency to find patterns even in random data, a tendency that served our ancestors well when spotting predators in the tall grass, but that can mislead us when we examine the subtleties of cosmic radiation. And yet the collaboration also acknowledged that the anomalies were real features of the data, not artifacts of the analysis, and that they warranted continued study and attention. And so the scientific community found itself in a curious position. Having mapped the cosmic microwave background with exquisite precision, having confirmed the broad outlines of the standard cosmological model with remarkable accuracy, and yet facing these persistent puzzles at the largest scales, these hints that something might be slightly off in our understanding of the universe, or perhaps in our understanding of the data, or perhaps simply in our statistical expectations. And the resolution of this uncertainty would require more work, more analysis, more observation, and perhaps entirely new ideas about the cosmos and our place within it. And this was not a cause for frustration, but rather a reminder that science is never truly finished, that every answer reveals new questions, and that the universe remains, in its quiet way, full of surprises for those who take the time to look. And so we find ourselves, quite naturally, wondering what might actually cause such a peculiar alignment in the oldest light we can see. It is a reasonable thing to wonder, And there is no shortage of ideas that cosmologists have considered over the years, each one examined carefully and thoughtfully, as scientists tend to do when faced with something unexpected. None of these explanations has won the day entirely, and that is perfectly all right, because science often proceeds this way, with many possibilities held gently open until the evidence tilts more clearly toward one or another. Let us begin with the most straightforward possibility, the one that any careful scientist would consider first, which is that perhaps we are simply looking through something that creates the illusion of alignment. Our own galaxy, the Milky Way, is not invisible to the instruments that measure the cosmic microwave background. It glows at many wavelengths, and its dust and gas emit radiation that must be carefully subtracted from the maps before we can see the primordial signal beneath. The solar system, too, has its own faint contribution, with interplanetary dust warmed by the sun producing a glow called the zodiacal light, and all of this must be accounted for and removed. The concern, then, is that perhaps some residual contamination remains, some subtle foreground emission that was not quite fully subtracted, and that this leftover glow might be creating the appearance of a preferred direction that is not truly cosmic in origin but merely local. It would be rather embarrassing, in a gentle sort of way, if the axis of evil turned out to be nothing more than insufficiently cleaned galactic dust, a bit of our cosmic neighborhood mistaken for a feature of the universe entire. This possibility has been taken very seriously indeed, and many different research groups have approached the problem with various techniques for foreground removal. They have used different frequency channels, different masking strategies to exclude the brightest parts of the galactic plane, different mathematical methods for separating components, and yet the alignments persist. The quadrupole and octuple continue to show their curious orientation toward the ecliptic and their alignment with each other, regardless of which foreground removal technique is applied. This robustness is both reassuring and puzzling. Reassuring because it suggests the signal is real rather than an artifact, and puzzling because it means we cannot simply dismiss it as contamination and move on with our evening. Some researchers have examined whether unknown systematic errors in the instruments themselves might be responsible, perhaps some subtle effect in the way the satellites scan the sky or process their data. But here again, the alignment was seen by WMAP and then independently confirmed by Planck, two missions with quite different designs, different orbits, different scanning strategies, and different data processing pipelines. For a systematic error to produce the same result in both would require a rather remarkable coincidence. And while coincidences do happen, they become less likely when the effect is reproduced so consistently. So let us set aside, for the moment, the possibility of foreground contamination and instrumental artifacts, not because they are ruled out entirely, but because repeated analyses have failed to eliminate the signal, and consider what cosmic explanations might account for a preferred direction in the microwave background. One idea that has been explored involves the integrated Sachs-Wolf effect, which is a phenomenon that occurs when photons from the cosmic microwave background pass through large-scale structures in the universe on their way to our detectors. When a photon enters a gravitational potential well, such as a region containing a large concentration of matter, it gains a small amount of energy as it falls in. Normally, it would lose exactly the same amount of energy climbing back out, leaving no net change. But if the universe is expanding and accelerating, as it appears to be doing, then the potential well becomes a bit shallower during the time the photon is passing through, and the photon emerges with slightly more energy than it had when it entered. This shows up as a tiny warm spot in the microwave background. The reverse happens with large voids, regions of space that are unusually empty of matter. A photon passing through a void experiences a slight net loss of energy and appears slightly cooler. Now, if there happen to be one or more truly enormous voids aligned in a particular direction from our vantage point, this could in principle create a pattern in the microwave background that might mimic an anomalous alignment. Several groups have searched for such supervoids and have found some evidence for large underdense regions in the direction of some of the cold spots in the microwave background, though the sizes and depths of these voids do not seem quite sufficient to explain the full magnitude of the observed anomalies. The integrated Sachs-Wolf effect remains a possible contributor to what we see, but it does not appear to be the complete answer, at least not on its own. Let us now venture into somewhat more exotic territory, where the possibilities become more speculative but also rather more interesting in a quiet sort of way. One class of explanations involves the global topology of the universe, which is to say the question of whether space might have a shape that connects back upon itself in some fashion, like the surface of a sphere but in higher dimensions. In the standard cosmological model, the universe is assumed to be infinite in extent, stretching away in all directions without end. But this is an assumption, not a proven fact, and it is entirely consistent with the equations of general relativity for the universe to be finite yet unbounded, wrapping around on itself in ways that might leave subtle imprints on the cosmic microwave background. The French cosmologist Jean-Pierre Luminet and his collaborators explored one particularly elegant possibility known as the Poincare dodecahedral space. In this model, the universe has the shape of a dodecahedron, a 12-sided regular solid, but with opposite faces identified with each other, meaning that if you could travel far enough in one direction, you would eventually return to where you started, having passed through what you thought was an exit only to find it was also an entrance. This is similar in spirit to the three torus topology, where the universe wraps around in all three spatial directions like a three-dimensional version of the screen in certain old video games where going off one edge brings you back on the opposite side. Such non-trivial topologies would affect the pattern of temperature fluctuations in the microwave background because the waves of density that created those fluctuations would have to fit within the finite space available, and certain wavelengths would be suppressed or enhanced depending on the size and shape of the universe. Luminet and colleagues suggested that a dodecahedral universe of just the right size might naturally produce a low quadrupole, and they noted that such a model could also produce alignments between large-scale features. The idea is beautiful in its simplicity and has a certain aesthetic appeal. The notion that the universe might be a closed and finite space, vast beyond human comprehension yet still bounded, like a great hall with walls that cannot be seen but which nonetheless exist. Searches have been conducted for the telltale signature of such a topology, which would show up as matching circles in the microwave background sky, patterns that repeat because light has had time to travel all the way around the universe and return. These searches have not found convincing evidence of such matched circles at the sizes predicted by the dodecahedral model, and most cosmologists now consider this particular hypothesis to be disfavored, though not entirely ruled out. The universe may still have a non-trivial topology, just one with a larger scale or more complicated structure than the simplest models suggest. Another avenue of inquiry considers the possibility that the universe itself might have a slight inherent anisotropy, a built-in directionality that has been present since the earliest moments. In the standard model, the expansion of the universe is assumed to be perfectly isotropic, proceeding at the same rate in all directions. But there are solutions to Einstein's equations of general relativity, known as Bianchi models, which allow for anisotropic expansion, where space stretches faster in some directions than in others. If the universe began with such an anisotropy, or if one developed during the inflationary epoch, it could leave a lasting imprint on the cosmic microwave background, manifesting as a preferred direction in the large-scale temperature pattern. Some researchers have fitted Bianchi model templates to the observed microwave background and found that certain anisotropic models can reproduce some of the observed features, including the alignment of the quadrupole and octuple. However, these models tend to require rather specific initial conditions, and they do not fit all the data perfectly. The consensus, such as it is, holds that standard isotropic cosmology is still the best overall description of what we see, but the Bianchi models remain an interesting theoretical possibility that has not been definitively excluded. At the most speculative end of the spectrum lie ideas connected to the multiverse, the notion that our observable universe might be just one bubble in a vast foam of universes, each with potentially different properties. In some versions of eternal inflation, our universe was born when a small region of space transitioned from a high-energy inflationary state to a lower-energy state, nucleating as a bubble that expanded rapidly to become everything we can see. If other such bubbles nucleated nearby in the inflating background, there is a small but non-zero probability that our bubble might have collided with a neighboring bubble at some point in the distant past. Matthew Kleben and his collaborators, among others, have studied what signatures such bubble collisions might leave behind. A collision would disturb the uniformity of our universe in a particular region of the sky, potentially leaving a circular or disc-shaped imprint in the cosmic microwave background, a region where the temperature pattern differs slightly from what we would otherwise expect. Some searches have been conducted for such collision signatures, and a few candidate features have been identified, though none with sufficient statistical significance to claim a detection. The axis of evil alignments are not a perfect match for the predicted bubble collision signatures, which tend to be more localized. But the possibility remains that some interaction with other regions of a larger multiverse might have left subtle traces in the pattern of ancient light we observe. It is a grand and somewhat dizzying idea, the notion that the strange alignment in our sky might be a message from beyond our universe, a cosmic postcard from a neighbor we can never visit or directly see. And so we are left, as scientists so often are, with a collection of ideas, each plausible in its own way, each capable of explaining some but not all of what we observe, and none yet commanding the full assent of the research community. The foreground contamination hypothesis has been tested and found wanting as a complete explanation, though it cannot be entirely dismissed. The integrated Sachs-Wolf effect from supervoids may contribute but seems insufficient on its own. Exotic topologies like the Poincare dodecahedron are elegant but appear to be disfavored by the data. Bianchi models with primordial anisotropy can fit some features but require special assumptions. And multiverse bubble collisions remain fascinating but highly speculative, with no confirmed observational support. Perhaps the truth lies in some combination of these effects, or in some idea not yet conceived, waiting to be discovered by a researcher who has not yet begun their career, or who is at this very moment staring at the data with fresh eyes. Or perhaps the axis of evil is simply a statistical fluctuation, an unlikely but not impossible coincidence in the random pattern of the cosmic microwave background, meaning nothing more than that the universe chose, by chance, to present us with this particular arrangement of hot and cold spots. Such is the nature of randomness, that even in a perfectly isotropic universe, any given realization of the fluctuations will have some pattern, some direction that stands out slightly from the rest, simply because pure featurelessness is itself infinitely unlikely. What we can say, with the calm certainty that comes from decades of careful observation, is that the cosmic microwave background remains one of our most powerful tools for understanding the universe, and that the anomalies within it, including the axis of evil, continue to inspire thoughtful investigation. Whether these features will ultimately teach us something profound about the nature of space, time, and cosmic origins, or whether they will fade into statistical insignificance as our measurements improve and our understanding deepens, remains to be seen. For now, they are simply puzzles, gentle mysteries in the ancient light, inviting curiosity without demanding immediate resolution. And so we come now to a quieter place in our journey, a place where the data itself begins to ask questions that reach beyond the instruments and the equations, into the very foundations of how we understand our place in the cosmos. For if the axis of evil is real, if this strange alignment in the cosmic microwave background is not a trick of measurement or a coincidence of statistics, but a genuine feature of the universe itself, then we must sit with the possibility that something we have long believed about the cosmos may need to be reconsidered, gently and carefully, the way one might reconsider an old assumption upon finding new evidence in a dusty archive. The assumption in question is sometimes called the Copernican principle, named not because Copernicus himself articulated it in precisely these terms, but because his work began the long process of removing Earth from the center of things. Before Copernicus, the cosmos was arranged with our planet at its heart, the sun and stars and planets wheeling around us in crystalline spheres, and there was a comforting geometry to it all, a sense that we occupied the most important place in creation. But Copernicus showed that the Earth moves around the sun, and in the centuries that followed, we learned that our sun is merely one star among hundreds of billions in a galaxy that is itself one among hundreds of billions of galaxies scattered across the observable universe. We learned that there is nothing particularly special about our location, that the same laws of physics apply here as they do in the most distant quasar, that the universe looks more or less the same in every direction and from every vantage point, at least when viewed on sufficiently large scales. This assumption of cosmic mediocrity, as it is sometimes called, has been extraordinarily successful. It allows cosmologists to treat the universe as homogeneous and isotropic, meaning that its properties are the same everywhere and in all directions, at least in a statistical sense averaged over very large regions. This assumption underlies the standard cosmological model, the mathematical framework that has explained the expansion of the universe, the formation of galaxies, the abundance of light elements forged in the first few minutes after the Big Bang, and the very existence and detailed structure of the cosmic microwave background itself. The model fits the data remarkably well across an enormous range of observations, from the local motions of galaxies to the faint ripples in the oldest light we can see. But the axis of evil whispers a different possibility. If there truly is a preferred direction in the cosmos, a special axis along which the largest patterns in the cosmic microwave background align, then the universe would not be perfectly isotropic after all. There would be a direction that matters, a cosmic north and south if you like, and this would be deeply strange because the standard model provides no mechanism for such an alignment. The physics of the early universe, as we currently understand it, should produce fluctuations that are statistically random and independent of direction. The hot and cold spots in the microwave background should be scattered without preference, like raindrops on a window, showing patterns at various scales but no overall orientation that spans the entire sky. A confirmed detection of such an alignment would not necessarily overturn everything we know, for science rarely works through sudden revolutions but rather through gradual refinement and occasional surprise. But it would require us to extend or modify the standard model in ways that we do not yet fully understand. Perhaps the topology of the universe is unusual, with the cosmos wrapping around itself in unexpected ways that would imprint certain preferred scales and directions on the largest patterns. Perhaps there are physical processes in the very early universe, in the moments of inflation or even before, that we have not yet accounted for and that left a subtle but detectable signature in the microwave background. Perhaps there is new physics waiting to be discovered, gentle and patient, hiding in the statistics of the oldest light. The philosophical implications are equally profound, though they unfold slowly and without drama, the way implications often do when one has time to sit with them. If the universe has a preferred direction, and if that direction happens to align with features of our local environment such as the plane of the solar system or the path of Earth's orbit, then we would face a peculiar coincidence that would require explanation. It would not mean that Earth is literally at the center of the cosmos, for the alignment involves directions rather than positions, but it would suggest that our location or motion is correlated in some way with the large-scale structure of the universe, and this would be surprising. Most cosmologists expect that any such correlation is either a statistical fluke or an artifact of how we process the data, removing the foreground contamination from our own galaxy and solar system. And this expectation is reasonable given how well the Copernican principle has served us. But the data continues to show the alignment, even after many careful attempts to explain it away, and so the question remains open. There is a concept that becomes important here, a gentle but significant limitation on what we can know, and it is called cosmic variance. The term refers to the fundamental statistical uncertainty that arises from the fact that we have only one universe to observe. When cosmologists make predictions about the cosmic microwave background, they predict not a single specific pattern but rather a statistical distribution of possible patterns, a range of outcomes that would be consistent with the underlying physics. If we could observe many different universes, each born from the same laws but with different random realizations of the initial fluctuations, we could compare the patterns and build up statistics with great confidence. But we cannot do this. We have only one sky to measure, only one set of largest scale patterns to analyze, and so we are somewhat limited in our ability to assess whether what we see is typical or unusual. This is especially true for the very largest patterns in the microwave background, the ones that correspond to the quadrupole and octuple and other low multipoles where the axis of evil appears most clearly. There are only a few independent ways to arrange a pattern at these scales, only a few degrees of freedom in the data, and so the statistical uncertainties are inherently large. It is a bit like trying to assess whether a coin is fair by flipping it only 5 or 6 times. You might get 3 heads and 2 tails, or perhaps 4 heads and 1 tail, and either outcome would be consistent with a fair coin even though the proportions differ from the expected 50-50 split. With more flips you could narrow down the answer, but with only a few flips you must accept a certain irreducible uncertainty. The low multipoles of the cosmic microwave background are like a very small number of coin flips, and so even a genuine alignment might be difficult to confirm with high statistical significance, and a statistical fluke might be difficult to rule out entirely. This limitation has shaped the debate among cosmologists for many years now. The anomalies were first noticed in the data from the Wilkinson Microwave Anisotropy Probe, and when the Planck satellite provided its even more precise measurements, many hoped that the improved data would either confirm or dismiss the strange alignments. The Planck collaboration released its final results in 2019, sometimes called the Planck Legacy Release, and the results were in some ways both satisfying and frustrating. The collaboration acknowledged that the anomalies remain present in the data and remain unexplained. The alignment of the low multipoles is there. The deficit of power at large scales is there. The asymmetry between hemispheres is there. And none of these features can be attributed with confidence to instrumental effects or foreground contamination. At the same time, the collaboration emphasized that the anomalies are not necessarily in conflict with the standard cosmological model when cosmic variance is taken into account. The probability of seeing such features by chance is low but not vanishingly low, perhaps a few %, and so reasonable scientists can disagree about whether this constitutes evidence for new physics or merely an unusual but not impossible outcome of a random process. The debate continues in papers and at conferences, where cosmologists gather to discuss the latest results and the various interpretations. Some researchers have championed the continued investigation of the anomalies, arguing that even a small probability of something unusual deserves attention, especially when the implications could be so profound. Among these researchers is Glenn Starkman at Case Western Reserve University, who has written extensively about the alignments and has argued that they may be telling us something important about the topology or geometry of the universe. Starkman and his collaborators have explored various theoretical possibilities, looking for models that could explain the alignments naturally, and they have called for the scientific community to take the anomalies seriously rather than dismissing them as statistical flukes. Other cosmologists take a different view, arguing that the anomalies are most likely just that, flukes of cosmic variance that happen to fall on the unusual end of the statistical distribution. They point out that when one looks at many different statistical properties of a data set, it is almost inevitable that some will appear unusual by chance, a phenomenon sometimes called the look elsewhere effect. If you examine 100 different properties and demand that each be consistent with expectations at the 95% level, then on average you would expect about 5 of them to appear anomalous even if nothing unusual is happening. The challenge is to determine whether the specific anomalies in the cosmic microwave background are genuinely unexpected or whether they are the kind of outliers that would be found in any sufficiently detailed examination of a complex data set. This disagreement is not a sign of crisis or confusion in the field, but rather a reflection of the honest uncertainty that remains when the evidence is ambiguous and the stakes are high. Cosmology has made tremendous progress in recent decades, measuring the age and composition and expansion history of the universe with remarkable precision, and the standard model continues to fit the vast majority of observations extremely well. The anomalies are a small and contested corner of this larger picture, and most cosmologists continue their work confident that the basic framework is sound, while keeping an open mind about the possibility that revisions may eventually be needed. What everyone agrees on is that more data would be helpful, and so the community looks forward to future missions that may shed new light on the old puzzles. One such mission is Lightbird, a satellite being developed by the Japan Aerospace Exploration Agency, known as JAXA, with contributions from international partners. Lightbird is planned for launch in the 2030s, and its primary goal is to measure the polarization of the cosmic microwave background with unprecedented sensitivity. Polarization is a property of light related to the orientation of its electromagnetic waves, and the polarization of the microwave background carries additional information about the early universe that is not fully captured by the temperature fluctuations alone. In particular, cosmologists hope to detect a subtle pattern of polarization called primordial B modes, which would be a signature of gravitational waves generated during the inflationary epoch, a period of rapid expansion in the first tiny fraction of a second after the Big Bang. While the search for primordial B modes is the main focus of LIGHTBIRD, the mission will also provide new measurements of the large-scale patterns in the microwave background, and these measurements may help to clarify the status of the anomalies. If the alignments persist in the new data, with independent instruments and different systematic effects, it would strengthen the case that they are real features of the cosmos. If the alignments fade or change character, it might suggest that they were influenced by subtle instrumental or analysis effects that differed between missions. Either outcome would be valuable, for science advances by narrowing uncertainties and constraining possibilities, whether or not the answer turns out to be surprising. And so we find ourselves in a curious position, living in a universe that may or may not have a preferred direction, that may or may not be perfectly isotropic, that may or may not require us to revise our understanding of our place within it. The uncertainty is not uncomfortable but rather fascinating in a quiet way, a reminder that even after decades of precision measurement and theoretical refinement, the cosmos still holds mysteries that we have not fully unraveled. The axis of evil may turn out to be a statistical coincidence, a trick of the data, a lesson in the limitations of what we can infer from a single universe. Or it may turn out to be a genuine feature, a clue pointing toward physics we have not yet imagined, a reason to extend our models and deepen our understanding. We do not yet know which of these possibilities is true, and so we wait, and we measure, and we think carefully about what the data is telling us, with patience and humility and a willingness to be surprised. And so we come now to a place of gentle conclusion, a moment to let the mind settle into stillness, to let all that we have considered drift softly into the background like the very light we have been discussing, that ancient glow that surrounds us even now, patient and unhurried, asking nothing of us but perhaps a quiet moment of wonder. It is worth remembering, as you rest here in the comfort of this present moment, that humanity has been studying the cosmic microwave background for barely 60 years, a span of time so brief that it almost defies comprehension when placed against the scale of cosmic history. 60 years is not even the length of a single human lifetime for many who walk the earth today, and yet within that slender window we have built instruments capable of detecting light that has been traveling toward us for more than 13 billion years. Light that set out on its journey when the universe was still a young and formless thing, filled with potential but not yet shaped into the galaxies and stars and planets that would one day give rise to creatures curious enough to look back and wonder at their own origins. 13.8 billion years. Give or take a few hundred million. That is the current best estimate for the age of our universe. A number so vast that it slips through the fingers of intuition like water through sand. If we were to compress all of cosmic time into a single year, with the Big Bang occurring at midnight on January 1st, then the cosmic microwave background would have been released sometime in the early hours of that same morning, perhaps around 1 or 2 in the morning on New Year's Day, and all of recorded human history, every civilization, every empire, every poem and equation and lullaby, would fit into the final second before midnight on December 31st. Our 60 years of studying this ancient light would occupy a fraction of that final second so small that it could scarcely be measured, a mere flutter of attention in the grand sweep of cosmic time. And yet here we are, in this impossibly brief moment, able to turn our instruments toward the sky and listen to whispers from the beginning of everything. There is something rather extraordinary about that, when you let yourself consider it without urgency or demand, simply allowing the fact of it to settle into your awareness like a leaf coming to rest upon still water. The cosmic microwave background will not always be available to us in this way, and this is perhaps one of the more quietly poignant truths of cosmology. As the universe continues its endless expansion, stretching space itself in all directions, the wavelength of this ancient light will continue to stretch along with it, growing longer and longer, fainter and fainter, until eventually it will be redshifted beyond the range of any instrument we could conceivably build. The photons will still be there, still traveling through the expanding void, but they will have become so diluted, so spread thin across the growing fabric of space, that they will fade into a silence too deep to hear. This process will take an immensely long time by any human measure, billions upon billions of years still remaining before the cosmic microwave background becomes truly undetectable. But the principle remains, that we exist within a window, a particular moment in cosmic history when this light is still bright enough to study, still rich enough with information to reward our careful attention. Earlier in the universe's history, before there were stars or planets or beings capable of building radio telescopes, there was no one to observe this light. And far in the universe's future, when the stars have burned out and the galaxies have drifted beyond each other's horizons, there may be no one who can. We happen to be here now, in this gentle interval between too early and too late, and there is a kind of quiet privilege in that. Not a privilege we earned or chose, but simply one that circumstances have granted us, like finding oneself awake during the most beautiful hour of a very long day. The image that arises from all of this is rather poetic, if you allow yourself to dwell upon it without rushing toward any particular conclusion. Imagine, if it brings you comfort, this ancient light arriving from everywhere at once, from every direction you might turn your gaze, from above and below and all around, a gentle embrace of radiation that has been traveling toward this very moment since before the Earth existed, before the Sun ignited, before the Milky Way had finished assembling itself from the primordial chaos of the early cosmos. This light carries within it the imprint of structures and patterns that existed when the universe was still a smooth and featureless sea of plasma, patterns that we can now detect with our instruments and translate into maps and statistics and careful measurements. And among those patterns, we find the curious alignments that have occupied our attention throughout this discussion. The strange way that certain features in the cosmic microwave background seem to know about our local position in space. The way that the quadrupole and the octopole seem to reach toward the same direction. The way that certain asymmetries appear where our models suggest there should be none. These are the whispers of structure that we do not yet understand. Messages written in a language we are still learning to read. And they arrive at our detectors with the patience of light that has waited more than 13 billion years to be noticed. Whether the so-called axis of evil represents genuine cosmic structure, some vast pattern imprinted on the universe at its birth that we are only now beginning to perceive, or whether it is merely a statistical fluctuation, a chance arrangement of random variations that our pattern-seeking minds have mistaken for significance, or whether it is something else entirely, some systematic effect of our instruments or our analysis or some aspect of physics we have not yet imagined, we cannot say with certainty, and it is possible that we may not know the answer for many years to come, or perhaps ever. But the asking itself, The careful formulation of the question and the patient gathering of data and the humble acknowledgement of what we do not know. This connects us to something larger than ourselves, to the universe's grandest questions about its own nature and origin and structure. Every time a researcher examines the maps of the cosmic microwave background and wonders whether these alignments are real, every time a graduate student runs another simulation or proposes another hypothesis or carefully checks another calculation, they are participating in one of the oldest and most fundamental human activities, the attempt to understand the cosmos that gave us birth. This is not a dramatic quest with a guaranteed conclusion, not a story with a villain to defeat or a treasure to claim, but rather a slow and patient accumulation of understanding, a gradual illumination of mysteries that may themselves open onto deeper mysteries still. And there is a kind of peace in accepting that, in allowing the questions to remain open without anxiety or frustration, simply resting in the presence of what we do not yet know and trusting that the asking is itself worthwhile. And now, as this narration draws toward its gentle close, perhaps you can allow yourself to drift for a moment among the stars, not rushing toward any destination but simply floating in the vast and patient darkness, surrounded on all sides by light that has been traveling since the universe was young. The cosmic microwave background fills all of space, a faint and ancient glow that we cannot see with our eyes but that bathes us nevertheless, and in a very real sense you are immersed in it even now, even as you rest here in comfort, even as your breathing grows slow and easy and your thoughts begin to soften at their edges. This light was present when the first atoms formed, when the universe became transparent for the first time and photons were finally free to travel without being scattered by the dense plasma that had filled all of space. This light has witnessed the birth of the first stars and the formation of the first galaxies, not by illuminating them but by traveling alongside them through the expanding cosmos, a silent companion to all of cosmic history. And now this light arrives at last at your small corner of the universe, carrying within it the subtle imprint of structures we do not yet understand, patterns that may hold clues to the deepest nature of reality or may simply be the beautiful noise of a universe too vast and complex to be fully captured by any model we can devise. Either way, there is a kind of comfort in it, in being cradled by the same light that filled the cosmos when it was young, in knowing that the mysteries we contemplate tonight have been waiting for more than 13 billion years for someone to notice them. You do not need to solve these mysteries to appreciate them, do not need to understand every detail of the cosmic microwave background to feel a quiet kinship with the universe that produced it. It is enough simply to rest here, to let the questions hover gently in the air around you without demanding answers, to allow yourself to be held by the vastness of cosmic time and space without feeling lost or overwhelmed. The universe is very old and very large, and we are very small and very brief, but we are made of the same matter that fills the cosmos, forged in the hearts of stars that burned out long before our planet existed. And the light that surrounds us now is part of our history too, part of the long chain of events that led from the Big Bang to this quiet moment, this peaceful pause in the endless unfolding of cosmic time. So let yourself rest now. Let your thoughts grow soft and distant. Let the mysteries of the cosmic microwave background drift slowly away like clouds dispersing after a gentle rain. The axis of evil, whatever it may be, will still be there when you wake, still waiting patiently in the data for someone to understand it, and the ancient light of the cosmos will still be arriving from every direction, still carrying its beautiful secrets, still whispering of structures and patterns that we are only beginning to perceive. You do not need to hear those whispers tonight. Do not need to solve any problems or answer any questions, only to rest here in the presence of wonder, cradled by the same light that has filled the universe since it was young, drifting peacefully among the stars, surrounded by mysteries that ask nothing of you but your gentle attention. And perhaps, in the quiet moments before sleep arrives, you might feel for just an instant the immensity of it all. The billions of years and the billions of light years and the countless photons arriving at this very moment from the edge of the observable universe. All of it converging here, in this small and precious moment. In this brief window of cosmic time when we happen to exist and happen to wonder. It is a rare and gentle thing to be alive in a universe that allows such wondering, and there is no need to grasp at it too tightly. No need to demand that it reveal all its secrets at once. It is enough simply to rest here, to let the vast and patient cosmos hold you as it has held all things since the beginning of time, to let the ancient light wash over you and carry you gently towards sleep, still carrying its beautiful mysteries, still whispering of wonders we have not yet imagined, still arriving from everywhere at once, soft and unhurried, asking nothing of you now but peace,